Okay. All right. So this week we're all talking about these experimental techniques, right? And so last class period we went over IR, which we use to see what in our molecule? Functional groups. And that's exactly the word that you want to have tied in your mind to IR. That's exactly what we use it for, is to figure out what the functional group is in our molecule. Today we're going to be moving on to nuclear, magnetic, resonance spectroscopy, more simply referred to as NMR. Okay? All right, so we're kind of break this lecture into these two parts. One is kind of the background, a little bit of a brief intro into how NMR works. And then the other half, kind of the bigger half, is going to be practically speaking, how do we analyze NMR spectra? All right, so first of all, let's just say NMR theory. Okay, so first of all, again, all of our spectroscopies have that same basic setup where you're sending photons in, measuring what comes back out. All right, NMR uses these really long wavelength photons, what we call radio waves. These are very long wavelength, which also makes them very low energy. Okay, to be honest, the fact this works at all is kind of a miracle. All right. What you're sending in is this very low signal, very low energy radio waves. They're being either absorbed or not by your, in this case, what's doing the exciting is our nuclei. In our atoms. Okay? This is part of what makes NMR so powerful, is we're not looking at bonds, but actually individual atoms within this molecule. Individual atoms will give us a signal on our NMR spectra, which is how we get so much information out of it, right? Because remember, whereas NMR, or rather IR, super easy to do, not all that much terribly information. NMR, more of a pain in the butt, but you get a huge amount of information, right? So this will help us determine our actual structure of our molecule. Right, by that I mean like size and shape. We put it in our IR, we know we have an alcohol, but do we have pentanol or butanol or what is it, right? That's what NMR is going to help us do. Okay, so let's try to tackle this. Why do these nuclei absorb photons? Okay, so if you remember back to when you were talking about electrons, that 1s2, 2s2 business, and you had those little boxes that you filled in with those arrows. You had to fill in one spin up and one spin down, right? One arrow pointing up, one arrow pointing down. And that was kind of your first introduction to this concept of spin. The idea that if two electrons are going to occupy the same orbital, they only can do so if they have different spins. All right? Turns out that all particles have this concept of spin associated with them. All right? So, all particles have what we call a spin, or what's more proper, angular momentum. All right, and this probably isn't if we hopped into our magic school bus and shrunk on down and we're actually looking at these particles, this might not be exactly what they're doing, but a helpful thing to kind of keep in mind is to imagine them spinning around like tops, right? So if you took like a dreidel or a top and you spin it around, it's sort of just sitting in place, rotating. That's kind of how we imagine our particles are doing as well. They have this intrinsic angular momentum to them. They're always spinning around, okay? So let's just make a little graph here. We're going to make a y-axis of energy. And an x-axis of magnetic field strength. Okay, I'm going to represent our spin up nuclei with a red up arrow, and spin down I'm going to represent in blue. Okay, so in the absence of a magnetic field, both spin up particles and spin down particles have the exact same energy. All right, but one key component of NMR, one thing that makes it kind of so difficult to use and so expensive, is you have to have this gigantic magnet as part of your machine. So you literally put, if you've ever seen an NMR, especially one of the large ones, they can be like the size of this room, kind of. Just this giant barrel. I don't know why I'm trying to describe it here. We have a picture. All right, it's like this giant barrel here. And what's inside that barrel is a humongous magnet, creating this really strong magnetic field. And you stick your sample right in the middle there of this giant magnetic field. Okay? They're kind of pain in the butt. Sometimes they have to have special rooms. You can't bring your credit cards or your phone in there, or it messes everything up. Nowadays, they've gotten some cute little tabletop ones. But anyways, bottom line is a big component of NMR is this big giant magnet. And the reason that they do that is because that will change the energy, where now my spin down are lower energy and my spin up are higher energy. All right, so let's say that we have a NMR that has a particular magnet. We'll say that our strength is right here. All right, so my nuclei is sitting, my spin down nuclei are right here at this energy. Okay? Well, in order for something to absorb a photon, it has to absorb the energy of that photon. And where is that energy going to go? So when we were talking about UV vis spectroscopy, it was exciting electrons from lower energy levels to a higher energy level. NMR is exciting the spin of these nuclei. So if we send in a photon, all right, this is our photon. What that's going to do is excite to a higher energy level that nuclei by flipping its spin. All right, so molecules will absorb these very weak radio waves. And why are they absorbing these radio waves? Because these radio waves are flipping the spin of their nuclei. All right? And yes, everybody's like, oh, totally. I totally see that. That's exactly what my guess was from the jump, right? No, this is very weird, bizarre quantum mechanics crap. The fact that a particle has a spin to begin with is not like a no-brainer concept, right? It takes a little bit of an imagination to sort of see what's going on here. But this is what NMR is doing. These radio waves are being absorbed, and they are exciting these spins from low spin to high spin, or from spin down to spin up. All right, so let's just kind of summarize here. All right, so in NMR, photons are absorbed because they excite the spin of nuclei. All right. It turns out that what's in the nuclei, the protons and the neutrons, they will pair up kind of like electrons as well. So if you have one proton and one neutron, their spins will cancel one another out. So this only works, NMR only works for atoms with an odd number of protons plus neutrons, what we call the mass number. All right, so just from like a sheer theoretical standpoint, not all nuclei are what they call NMR active. They have to have this odd mass number. If you sum together the number of protons and the number of neutrons, you got to get an odd number. Cool. So the world of NMR is a little bit more vast than this, but generally speaking, and a good introductory point for your organic chemistry course is to discuss two different types of NMR. Carbon-13 NMR and then hydrogen-1 NMR. All right, and we're going to start with carbon-13. It's not my favorite at all, but it is a little bit simpler, and so it's a good starting point here. All right, so C13 NMR. This is when you're exciting those carbon-13 nuclei. All right. Carbon-13 is by far the most rare isotope of carbon, right? More common is carbon-12. That's what most of the carbon is. So when you have a sample, you only have a very small number of molecules that contain those carbon-13 atoms to begin with, which is, again, one of the pain-in-the-butt limitations of NMR, is you have to have a relatively high sample concentration in order to get a good signal. The signal that you get, period, is pretty weak because you're starting out with these very weak radio waves, and then you add on top of that the fact that only like 0.1% of all carbon is carbon-13, so you got to have a pretty high sample concentration in order to get a good signal. One of the ways that they can get around that is you can actually use like isotopically, you can buy like pure carbon-13 and make your molecule with that. And it costs about $1 gajillion to do it, all right? So again, just kind of limited by the practicality here. But nonetheless, if you can get a sample concentration pretty high, which works great for say like a pure liquid, like an alcohol, right? You'll be exciting this carbon-13 NMR or nuclei. All right, so let's just say C13. Very rare. We need lots of sample, high concentration of our sample. All right, so thinking about an NMR spectra and how we analyze an NMR spectra. All right, there's going to be two sort of things that we're going to make note of. One is what's called the chemical shift. All right, that's simply where on the x-axis we see this peak. Okay, So actually, I lied. Let's take a step back. Let's take a look at just an NMR spectra here. What does this look like? All right. So this is the kind of graph that you would expect to see from NMR. We have a x-axis here of chemical shift values. These are just very similar to a wavelength like what we saw in our, or rather a frequency like what we saw in our IR spectra. It just tells you the different photons chemical shift that you're sending in. And we see we got these peaks here. Boom, boom, boom. Okay? So we get this graph, ideally a nice flat baseline, get a nice clean signal, and a bunch of peaks. And then we have these little values on top here. Okay? So again, our x-axis is what we call a chemical shift here. So where on the x-axis? And this gives you two very important pieces of information about your compound. All right, so first of all, where on that axis your peak is. That gives you information about the chemical environment of that carbon. I.e. the types of bonds that that carbon has. Okay, so it turns out that a double bonded carbon will absorb in a different place on our spectrum than a single bonded carbon, than a carbonyl carbon, et cetera, right? So where exactly on that x-axis gives you information, okay? But a very important piece of information is how many peaks you see. Okay, this tells you the number of what we're going to call chemically distinct carbons are in your molecule. All right, by chemically distinct, we mean a completely unique chemical environment. All right, so we're going to take a second and talk about how we spy chemically distinct carbons in a molecule. Okay, so first of all, when we go and we look at that chart where we analyze our NMR spectra, first thing we're going to do is look and see what peaks we have in terms of their chemical shift. Where they are on the x-axis tells us information, but more importantly, not more importantly, but honestly very importantly, how many peaks tells us the number of chemically distinct carbons. Sometimes the only thing you have to pay attention to are the number of peaks that you see, and that's enough to narrow it down as to what your molecule is. All right, so what do I mean by chemically distinct carbons? All right, so by chemically distinct carbons, I mean how many carbons are in a completely unique chemical environment all right, by chemical environment, I mean all of its neighboring carbons and bonds. Well, I guess neighboring all bonds. All right, and this is one thing where I really don't know that the definition is all that helpful. What's going to be, what we're going to need to do is kind of learn by analogy here, but just go through a bunch of examples, all right? And really what we're sort of going to be paying attention to is the symmetry in a molecule. Okay, so let's take a simple example here. This is, of course, propane. All right, propane has these 3 carbons in there. All right, but it only has 2 chemically distinct environments. It's got these 2 methyl groups here that are both in the same group. All right, that is because they both share just this 1 carbon in the middle here. All right, and again, the easiest way to see this idea of chemical distinction is to look for symmetry, either rotational symmetry or reflective symmetry. The fact that I can fold this molecule in half along this axis right here lets me know that these 2 carbons must be in the same group. Right? There's no chemical distinction between those 2 carbons. If you look at, if we are standing right here, looking this way, our molecule looks, that carbon over here looks the exact same as if we were to instead stand on this one and look this way. That's an eyeball, believe it or not. Okay? All right, so these 2 environments are the exact same. Same chemical environment. All right, and then this one is off in its own. So if I were to take the carbon-13 NMR spectrum of propane, I would expect to see 2 peaks. One corresponding to the orange group of carbons, one corresponding to the red carbon. Okay? All right, so let's just practice this. I'm going to draw a molecule, and you're going to tell me how many chemically distinct groups of carbons there are in that molecule. All right, let's do benzene first, actually. How many chemically distinct groups of carbons do we see in this molecule? Does it have any symmetry? So I can take this thing and pick it up and rotate it and perfectly superimpose it. All right, I can rotate it every which way and superimpose it. So this only has one chemically distinct groups of carbons. Well, I'm just going to say one. Okay, so then based on that analogy, what about cyclohexane? How many chemically distinct groups of carbon would that have? Again, just one, right? Because it's got that rotational symmetry. What about pentane here? How many chemically distinct groups do we see? Somebody give it a shot. Three, cool, awesome, yeah. So, importantly, pentane has this plane of symmetry going right down the middle here, right? And so the ones that are mirror image of one another have to be in that same group. So these ones on the end are the same group. These ones in the middle are the second one and fourth one here in the same group. And if it lies on that plane, then it's all by itself. Okay? Now, this is an important distinction, rather important thing to keep in mind with regard to chemically distinct. Notice that both the green group are CH2s and the purple group is a CH2. Right? That alone is not enough to make you chemically distinct, right? These two carbons will still, or rather these two groups will still absorb pretty close together, but in slightly different places on our spectrum because they're not in the exact same environment, right? So that's what makes NMR so powerful, is exactly where something's going to absorb is super sensitive to the exact chemical environment that it's in. So if it's not in the exact same environment, it's not going to absorb in the exact same place. All right? So then how many peaks would we expect to get on our NMR spectrum for pentane? Three, right? One for each of those chemically distinct groups. All right, and then what about butane? This one's a little bit harder to see. Anybody got a guess? It is two. All right, so we have this methyl carbon, and then this one right here. Let's all convince ourselves that these are definitely not in the same group, right? Okay, so how can I see that there are only two? Well, let's pick this thing up and then rotate it. And now we can superimpose. And look, that red group, that third carbon is also in that red group. Exact same environment. That orange carbon is also in that same group, exact same environment, right? So for butane, we would expect to see two chemically distinct groups of carbons, two peaks on our spectrum. Okay, you can actually also draw butane in such a way where you could see its plane of symmetry differently, right? We can always rotate about our single bonds. So this is also a butane. Okay, either way you want to look at it, whether you do the rotational symmetry or the reflective symmetry, you can see that those are only two chemically distinct groups. Cool. All right, we'll practice that a bunch more. One more thing, though. Let's go back to this benzene cyclohexane thing here. We said that both of these are only going to give one peak on our NMR spectrum. So then how could I distinguish between whether I have benzene or whether I have cyclohexane? Remember that first piece of information that we were talking about, where they absorb. All right? Your textbook or lab manual or whatever it will be will likely have some sort of a graph, some sort of an image that looks like this, which tells you, roughly speaking, the range in which you can expect to see certain signals. So it turns out that our sp3 hybridized carbons are going to absorb down here between 0 and 50. The special carbons with their heteroatoms, or if there's a carbon-carbon triple bond, will be between 50 and 100. Your sp2 hybridized carbons are easy to spot because they always lie in this region up here. And then carbonyl carbons are always at the far end of your spectrum up here, okay, between 150 and 220. So importantly, for both cyclohexane and benzene, I would expect to see only one peak, but my cyclohexane peak would be all the way down here on my spectrum, whereas my benzene peak would be all the way up here on my spectrum. All right, so again, two pieces of information that we get from that sort of looking at that x-axis, where on the spectrum it lies and how many there are. Now let me just say, I made a big mistake, or I feel like I made a mistake when I was analyzing NMR as a student to focus so heavily only on this part right here, where it lies, all right? But there's always like a little bit of wiggle room. Look, that's a pretty wide range there, 50 ppm in terms of that shift. Things might be a little bit more to the left or to the right than what you'd expect. That, how many peaks there are, again, is like one of the most important pieces of information, telling you how many chemically distinct groups of carbons. Sometimes that alone is fine. You don't even have to pay attention to where they are on the spectrum. Just how many there are is a huge piece of information, all right? So anyways, I'm not saying this is worthless. It's definitely important, but don't like solely focus on this portion right here, where it's expected to be absorbed. Okay, so then there's one more thing that we got to talk about. We talked about our chemical shift. That's the first thing we do when we analyze our NMR, right? We say how many peaks there are and where they are on that x-axis. But we're also going to get another piece of information, which is what's called the integration of those peaks. I know everybody's like, I know exactly what integration is because I've taken calculus, simply the area under those curves. All right, so we're all caught up on our multivariable calculus, right? No, I'm kidding. We're not going to do any calculus. But basically, you put this graph in a computer, you say integrate these peaks, and it gives you this value for each peak, which is a ton of information, okay? Your integration tells you how many carbons are in that chemically distinct group. Okay, so what do I mean by that? Let's go back to our example of pentane here. All right, we said that we're going to have 3 peaks. Our orange peak, our green peak, and our purple peak. All right, so we got 3 peaks here, each corresponding to one of these chemically distinct groups. All right, these peaks are also going to differ in their integration. I have 2 carbons in that orange group, so I'm going to expect an integration value of 2 for that orange group of carbons. All right, what about my green group? What would my integration value be? Also 2. And what about my purple group? Just 1. All right. So what we would see in our NMR spectrum of this molecule here, if we do chemical shift, we're going to get 3 peaks. They're all going to be pretty far down. 2 of them are going to be twice as tall as the third one there. Twice the amount of area, but they tend to be pretty sharp peaks. So height is a good approximation. All right, one of them is going to correspond to that orange group. Another one's going to correspond to that green group. And then the last one, that one that's half as tall, would correspond to that purple group. Cool. All right, so let's just take a look at some structures here. And we're going to try to figure out how many peaks we would expect to see. I guess we already did benzene. How many peaks would we expect to see? Just one. And again, because benzene is these sp2 hybridized carbons, we would expect to see them kind of far up on our graph here between 100 and 150. And boom, there it is. Okay. What about ethane? How many peaks would we expect to see? Again, just one, right? We got that plane of symmetry right down the middle. All right, but these would be where on our spectrum? On the left or the right? All the way downfield here. Or upfield? I don't remember. All right, all the way at the low ppms. Okay. What about this carbon, this molecule here? Everybody take a second and see if we can't figure out what our spectrum should look like. How many chemically distinct groups we should have for this, what is this, 3-hexyne. Anybody got a guess? 3, so we have these two. Again, we can rotate this molecule to prove it to ourselves. These two, and then these two. Okay. Where would we expect to see these peaks on our diagram? Let's look at this little chart here. Okay. 2 of those peaks are just these sp3 hybridized carbons. And then one of them is that special sp hybridized carbon in that triple bond. All right, so if we look at our spectrum here, we got 2 peaks all the way on this end and 1 sitting in that triple bonded region, right? This one corresponds to that purple carbon. Over here, you can't really, I mean, I'm sure there's a rule for methyl versus the internal that I don't know, but we're just going to assign them. One of them's green, one of them's orange. Should probably know that. All right, and then lastly, if we do acetone, all right, how many chemically distinct groups of carbons do we have? So we got these 2. Again, we have this plane of symmetry right down the middle of this molecule. Importantly, is that oxygen going to give us a peak? No, right? So we're looking specifically at carbons, carbon 13s. So I have 2 in this orange group and then 1 in this green group. All right, so first of all, where on the spectrum would we expect these to absorb? If we look back at our little cheat sheet here. All right, my orange group, my methyl group, is going to be somewhere over here. But that carbonyl carbon is going to be all the way on this far end here. Okay? Not only that, but let's think, what about the integration? What about the size of these peaks? How should the size of the orange peak compare to the size of the green peak? So orange should be twice as large, have that integration value that is twice that of my green peak. And so that's exactly what we see. Okay? So these are these big pieces of information that we get from our NMR spectra. Where they absorb on the spectra is going to tell us about the chemical environment of those carbons. Most importantly, the number of peaks that we see tell us how many chemically distinct carbons there are, which again is like one and the same as saying about the symmetry of your molecule. And then that integration value tells you just how many carbons there are in that group. All right. So last thing we're going to do, we're going to take a look at 4 alkyl halides here, all right? And I want you guys to try to assign spectra to each of these compounds here. Okay? We could just, for a second, zoom in. I'll just make note, first of all, we're very zoomed in on this particular region between 0 and this is 80 up here, but we're all the way on this region of our spectrum. kind of zoomed in here, right? Because we only have these sp3 hybridized carbons in this case. Okay. The other thing we can make note is of those integration values. So everybody take a second and copy these structures down, and then I'll kind of zoom in a little bit more on our spectra so you can see them a little bit easier. All right, but our goal here, spectra A, B, C, D, assign them to one of these 4 alkyl halides here. Should be good and put in lone pairs. All right, so if we all got our structures, I'm going to zoom in so we can see a little bit easier here. All right, and let me just give you a little bit of a hint here, or a little bit of help. A good place to start is with your options up top here, right? Look at each of these and determine how many chemically distinct groups of carbons there are. Once you find out how many chemically distinct groups there are, try to assign an integration value to each group. All right, that will help you better understand how to read or how to match them to these NMR spectra here. All right, so let's do this. So let's go through and assign how many chemically distinct groups of carbons do we see in this molecule right here? 4, right? None of these are the exact same. This isn't regular old butane where I can rotate it and get the same thing because I have that chlorine on carbon 2 that's messing up my symmetry. So every single one of these is going to fall into its own chemically distinct group. And so boom, I don't have to do anything else. Which spectrum does that correspond to? Let's call this A, B, C, and D. C, right? So again, that number of peaks is a huge amount of information in terms of what your compound can be. Okay? If we go down the line here, how many chemically distinct groups of carbons do we have here? This is a tough one to see because it, based on like this flat projection of this molecule, it's a little bit harder to see. But remember, this flat projection is of a tetrahedral geometry where all of these 3 carbons are going to be in the same group. And then we got one in the middle here that's different. All right, cool. Let's skip over this guy for a second and go here. How many chemically distinct groups of carbons? Also 2. So I have 2 spectra, A and B, that both have these 2 peaks. Both indicate there are 2 chemically distinct groups of carbons. So now, how am I going to figure out what's what here? The integration value, right? So in spectrum A, I have 1 carbon in this peak and 2 in this peak, whereas in spectrum B, it's 1 and 3, right? And I can see in this molecule there are 3 carbons in that orange group. So this will be my, what is that? Tert, butyl, something? Chloride, there it is. We got there. All right. And then the last one, well, process of elimination, but also let's convince ourselves that this has these 2 chemically distinct groups. Or 3 chemically distinct groups, I'm sorry. 2 of them with 2 carbons in them, and 1 of them with just 1. So that's going to correspond to our last spectrum here. Cool. All right, next time we'll go over H1 NMR, which is very, very similar with 1 extra piece of information.